problem 5, we have to find out the values of m, for which the first case y equal to e raised to mx is a solution of this differential equation y double prime plus y prime minus 6y equals to 0. And in the case when y equal to x raised to m, for x strictly greater than 0, is a solution of x square y double prime minus 4xy prime plus 4y equal to 0. So one of the most natural things to do is to substitute the value of y over here, because it is given to us that this satisfies this equation. So let us do that. So substitute the solution e raised to mx into the ordinary differential equation, and by that we get this. The double derivative of e to the mx is m square e to the mx plus derivative of e to the mx is m times e raised to mx minus 6 e raised to mx equal to 0. Okay, or it can be written as this. Why so? You just take e raised to mx common from the left hand side of this equation, and you're left with e raised to mx times this particular term is equal to 0. But since e raised to mx is never equal to 0, it follows that m square plus m minus 6 equal to 0. Now we can easily find out the values of m. This would imply that m plus 3 times m minus 2 is equal to 0, which gives that m is equal to 2 and minus 3. So we have got the values of m for which a holds. Okay. Next we do the same thing for the part b. We substitute x to the m into the given ODE, and we get this. Now here we take x to the m to be common. Okay, x to the m times this is equal to 0, but because x is strictly greater than 0, so again x to the m cannot be equal to 0. So therefore it forces this particular thing to be equal to 0, and this gives the values of m to be 1, 4. Alright, so in this case we have found the values of m for which these two holds. Okay. We have just used the fact that if some function is given to be solution of this, then by definition it satisfies the equation. The next problem, let phi I be the solution of y prime plus ay equal to bix for I equal to 1, 2. We have to show that phi 1 plus phi 2 satisfies the equation y prime plus ay equal to b1x plus b2x. Use this result to find the solutions of this equation passing through the origin. Okay, so the first part is very clear actually. Why is it clear? Because see, we have to use here one important property of the derivative, that is the following: the derivative of addition of two functions is equal to the addition of the derivative of the two functions. Okay, so by using that here, we know by definition, just now how we saw, by definition we know that phi 1 and phi 2 will satisfy this, and now we need to check if phi 1 plus phi 2 satisfies this equation or not. So for that, what do? We just plug in phi 1 plus phi 2 instead of this. Okay, and then we will see by using the given equation and that the fact that phi 1 and phi 2 are solutions of this, and using the property which I mentioned just now, it will follow at once that phi 1 plus phi 2 satisfies this equation. Okay, so for the second part, you see y prime plus y is equal to sin x plus 3 cos 2x. You have to find out the solution of this. So we need to break it up into two parts, so into three parts in fact. So the first part is y prime plus y equal to sin x, y prime plus y equal to 3 cos 2x, and y prime plus y equal to 0. And we have to add up these solutions, right, by using the property that we just now proved verbally. Okay. So what we'll do is we'll find out the individual solutions in all the three cases, and we'll just add them up, and that would give us the solution of the required differential equation. and then we'll see what condition we need to impose in order to know that the solution passes through the origin, in order to force this condition. Okay, let's see. So here we have to make a trial or a guess. So here you see that these have constants, these dependent variable, they are constant, they have constant coefficients, and we can clearly see that in the first case, we are looking at solving the first case now. In this case you see that derivative of sine is cos, okay, derivative of cos is minus sine. So we can see that we can play with the coefficients alpha and beta, okay, and expect that this to be a solution of this, and we'll play with the constants and we'll see what are the conditions on these constants, but it is reasonable to attempt this as a trial solution because of this. Okay, and please keep in mind that the dependent variables and the derivatives have constant coefficient, okay, in all the cases. So let us begin this. So we just substitute this into the differential equation and we get this. Okay, so here you see we have substituted, we have assumed this to be a solution. So y prime would be minus alpha sine x plus beta cos x plus y, that y is alpha cos x plus beta sine x, that is given to be equal to sine x. Okay, so we have to compare the coefficients on both the sides of sine and cos. You collect the terms of sine x, collect the coefficient of sine x and the coefficient of cos x on both the sides, and that gives us these two conditions on alpha and beta. So we get beta minus alpha equal to 1 and alpha plus beta equal to 0. So in this case we get beta to be equal to 1 by 2 and alpha to be equal to minus 1 by 2. So we substituted back in this. So we had assumed that the solution is of the form alpha cos x plus beta sin x, and we have seen that after substituting this turns out to be the solution for the differential equation 1. Okay. Likewise, we seek a solution of the second part, that is y prime plus y equal to 3 cos 2x. So here we seek the solution in this form, okay, for the same reason. The derivative of sin x is sin 2x is 2 cos x, okay. Similarly, the derivative of cos 2x is minus 2 sin 2x, okay. So again we see, and in a similar fashion we proceed to know that the final solution of the part 2 will be equal to this. Okay, you have to just do it in a similar fashion as above. You have to compare the coefficients on both the sides. You would then get to the coefficients. You would then be comparing the coefficients of cos 2x and sin 2x on both the sides, and then you get solution this. Okay, hence a general solution of the ODE is this. Okay, from where this is appearing, please note that there was even a third part involved here. Okay, so in the third part we need to find out the solution of this and even add this up. So this term takes care of this. Okay, this is clearly solution of the third part. You have to do it just by integration. You just integrate it once and you get this. But now the main thing is that we need to, this c is the constant of integration. Okay, this can be removed by the condition that is given to us. It is given to us that this should be passing through the origin. So passing through the origin means x equal to y equal to 0. So once we substitute that in this case, we get exactly, see, sin 0 is 0, okay, cos 0 is 1. Again here sin minus cos, so it would be 0 minus 1, so minus 1 by 2 plus 3 by 5 plus c is equal to 0. And this gives us the value of c, which is equal to minus 1 by 10. Okay, and we go on to substitute this value here, which gives us the final solution. Okay, so this finishes the problem 7. Now let's move on to the last problem of the day. Okay, problem 8. So in this case we have to obtain the solutions of the following differential equations: y prime equal to y cot x, where y of pi by 2 is equal to 1, and the next one y prime equal to y minus x whole square, where y of 0 is equal to 2. So we look at the second part first. Okay, so here we have to just separate the variables. So by variable separable method and integrating this, we directly get ln y equal to ln sin x plus c, where c is the constant of integration. So we need to remove this by substituting this. Okay, using the initial conditions that are given, we get c to be equal to 0, and once c is equal to 0, then taking exponentials on both the sides, we get y is equal to sin x. Okay, the next problem, the sixth part, the given equation is this. Okay, and it can be written as this. You can just see the derivative of this. What is the derivative of this? It is y prime minus 1. Okay, y prime minus 1. So here just put minus 1 on both the sides. Okay, so it is same as this. Okay, to just open this up to get this. These two are just equivalent equations. Now substitute y minus x to be equal to u. So we are going to solve this differential equation by the method of substitution. So we substitute y minus x to be equal to u, and then we convert this differential equation in terms of u. So which gives us u prime equal to u square minus 1. And now the condition would change. Here the condition given was y of 0 is equal to 2. That means when x is equal to 0, y is equal to 2. So when x is equal to 0, what would u be equal to? U will be equal to 2, because then u will be equal to 2 minus 0, which is equal to 2. So this is the initial condition that is imposed on this differential equation, wherein the dependent variable is u instead of y. And now it is just a matter of one line to solve this differential equation. You have to just separate the variables and integrate to get this. Okay, and hence you put 2 to that side, and you take exponentials to get a different constant of integration, which we call as c tilde, where c is found to be 1 by 3. How is c found to be 1 by 3? Please note that u of 0 is equal to 2. So to just substitute x to be 0 and u to be equal to 2, that will give the value of c tilde, and therefore finally the solution is exactly given by this. Okay, u is equal to this. So this finishes the problems of tutorial 1.